So this is the page number 22. We can see here the diagram of 800 megawatt monoblock unit. Steam generation capacity is 2650 tons per hour. Steam temperature is 545 degrees Celsius. Steam pressure is 25.5 meganewton per meter squared. And T-shaped in layout, it has its boiler structure suspended from the boiler room. We can see in the middle column burner. So from the burner, the flue gases going through the all welded water walls and lower radiation section and upper radiation section. Then the flue gas traveled to first Platen superheater, second Platen superheater, third Platen superheater, and final bank of reheater. After that, the flue gas travel. After that, the superheater travel to the left and right columns in both are same as first stage convective superheater, supercritical pressure, then first preheater stage, then economizer, then it is going to the flue gas to air preheater. We can see in the left hot flue gas to cold mill. That's it. The next diagram is figure 1.17, 1200 megawatt monoblock unit TGMP 1202. It is Russian designed boiler. Gas and fuel oil fired boiler of suspended design generates 3950 ton per hour of supercritical pressure superheated steam. In here we can see in the left column burners are there. From the burners, flue gas is traveled through the lower radiation section, upper radiation section, then Platen superheater, convective superheater first stage, convective superheater second stage, then reheater bank for last stage. After the flue gas is going through the reheater control stage, economizer. Then hot combustion products to air preheater. So in both diagram, air preheaters are not shown. In between the Platen superheater and convective superheater first stage, slack screen is also there. So this is the question: what are the disadvantages of fluidized bed boilers or as compared to pulverized coal-fired boilers? Answer is the feed stream of solid fuels must be closely monitored and sized properly. Combustion efficiency is usually poor at low loads. When burning low-grade fuels, particularly those containing salts, care must be taken to maintain accurate bed temperature over AFT. Otherwise, the salts may melt at the bed temperatures or may produce atectics in the bed, causing bed seizure and loss of fluidization. In-bed tube erosion is higher. For utility units above 200 megawatt, any economy of scale disappears for bubbling bed boilers, owing to the fact that bed plan area requirements exceed the practical limits. CFB is handicapped by the same problem. It is height limited as unit output increases due to the large amount of solids that must be circulated through the furnace. After this height limit is reached, the designer must increase the bed plan area to accommodate greater heat transfer surface requirements. And from a practical point of view, this is not affordable. Next one, pulverized coal-fired convectional boilers register high efficiency than fluidized bed boilers of unit above 200 megawatt. The efficiency gain is about 1.5%. PC fired boilers required at least half the limestone requirement of fluidized bed boilers for equivalent sulfur arrest. Last, the most nagging drawback with fluidized boilers is that they produce a substantial quantity of solid waste ash that must be safely deposited off. Some experts believe that the quantity of even greater than the form a conventional pulverized coal-fired boiler badified with a wet limestone scrubber at equivalent conditions. These are the disadvantages of fluidized bed boilers. Next question. Why is the quantity of ash produced by a FBC unit greater than a conventional pulverized coal-fired boiler fitted with wet limestone scrubber at equivalent conditions? Answer. This is mainly due to the fact that whereas a wet scrubber can operate a calcium to sulfur ratio close to 1.0, an FBC unit may require anywhere from 1.5 to 3.0. Next question. How can fluidized bed boilers classified? All fluidized bed boilers can be categorized into two main groups depending on mode of operation of the fluidized bed. These are atmospheric fluidized bed AFB boilers, pressurized fluidized bed PFB boilers. AFB boilers can be two types: atmospheric bubbling bed boilers, atmospheric circulating bed boilers. AFB boilers can be subdivided into bubbling bed with inbed tubes, bubbling bed without inbed tubes, circulating fluidized bed with external heat exchangers, circulating fluidized bed without external heat exchangers. A distinction can also be made on the basis of fluidized velocity of air, which is fundamental distinguishing feature of fluidized bed combustion units. Bubbling bed have lower fluidization velocities 1.2 to 3.6 meter per second so that particles do not escape from the bed illustration into the convective passes. CFBs apply higher velocities 3.6 to 9 meter per second and in fact promote solid electrations. Next question. What are the principal attributes of atmospheric fluidized bed units? Answer. In a typical AFB combustion unit, solid, liquid or gaseous fuels, particularly coal plus solid waste fuels, means coal, municipal waste, etc., together with inert material, means silica, alumina or ash, and sorbent such as limestone are kept suspended in the combustion chamber by primary air distributed below the combustor floor. Turbulence is promoted by fluidization that turns the entire mass of solids into something like a liquid. Owing to improved mixing, heat generated at a substantially lower and more uniformly distributed temperature, typically 810 degree to 870 degrees Celsius, than stoker fired units or pulverized coal fired boiler. Thus, given the properly sized combustion chamber, the heat release rate will be at a level comparable to convectional boiler but a lower temperature and theoretically without any loss of efficiency. The operating temperature 810 degree to 870 degrees Celsius of an FBC unit is well below the formation of thermal NOx. Staged combustion can be applied to minimize the formation of fuel-borne NOx as well. The operating temperature range is such that the reactions of SOx with the suitable sorbent, commonly limestone, are thermally balanced. The fluidization mechanism leads to less volatilization of alkali compounds. Added turbulence minimizes the chances of a hot spot on the boiler and shell surfaces. Less sensitivity to quantity and the nature of ash. Smaller furnace volume. We can see the diagrams in the next video. Thank you.